Good morning, everyone. Welcome to this webinar on deploying high-performance containers with Sarus on Piz Daint. My name is Alberto. I am a software engineer here at CSCS. And together with me, we also have Theophilos, who will be moderating the chat and answering your most burning questions, even that you can ask on the chat, but I really hope that we will have time for some proper Q&A after the presentation. So today I'm going to talk with you about how to use Sarus, which is one of the container tools available on our flagship system Piz Daint, to deploy containers which can effectively leverage high performance hardware that we have available on our supercomputer. Sorry about that. First thing first, it is worth mentioning that this webinar is supported by the EuroCC project, which is a European project working to create a network of national competence centers all across the continent, with the ultimate goal of fostering and increasing the adoption of HPC technologies. So if that sounds interesting, you should check this out. Let's get to the meaty stuff. How do I want to structure this webinar? First, I will be providing an introduction, a quick introduction to Sarus, also providing some highlights from a user perspective. Then we'll provide some tips for running MPI and GPU containers on Piz Daint. And then we will get to some actual examples on Piz Daint itself. I have selected three examples. First, the Ozu Micro Benchmark to showcase some MPI usage, and we'll go over a CUDA SDK sample for some for GPU usage, and then we'll put those aspects together to run a real-world application. In this case, GROMACS, where we will also have to exchange data into and out of the container. So some data I/O, and as I mentioned, we will have some time for a Q&A after that. So Sarus is a container engine focused on HPC with the main purpose of combining container portability with native HPC performance. What does that mean? It means that if you take a portable container image, so an image with generic components, non-hardware specific software, so an image that you can run across a variety of different systems, you take that image, and starting from that portable image, Sarus will do everything it can in order to create a container that can leverage to the fullest the underlying hardware of the HPC systems you are running on. So you start with a portable image, but you end up with a high performance container. In order to do so, Sarus integrates with the HPC infrastructure and software. Think about parallel file systems, accelerators, workload managers, the usual suspects, I would say. And it will also customizes containers at runtime with standard plugins. So Sarus always maintains a significant degree of flexibility and configurability throughout its installation. Sarus is also meant to be convenient for the users to adopt, and so it builds upon the popularity of Docker by being able to pull regular Docker images. So you don't need to adopt more container tools or even exotic tools to build newer images. You can just reuse what you built with Docker. And also Sarus provides a Docker-like command line interface so to ease the transition into this when using this new tool. This is a representation of the typical user workflow we see at CSCS when using containers. Users start by creating a Docker image on their laptop or a personal workstation. Then they upload the image to a remote registry, for example, Docker Hub, which is the biggest and most popular one. Then the image is pulled into the storage at the HPC center and then deployed at scale on the HPC system. And within this workflow, Sarus can perform steps 3 and 4. So the pull and then the deployment, of course. From a user perspective, Sarus offers a consistent experience with Docker by virtue of the closely resembling command line interface, but also with the host environment, because the environment variables, user identities, and file permissions, all those properties are preserved when moving into the container. So it's really a familiar experience and a transition between host and container that is as seamless as it can be. Sarus is, as I mentioned, Sarus is able to pull images from Docker registries, think Docker Hub, and also NVIDIA NGC, Quay.io, or others, if you know them. If you are uncomfortable with uploading your images to a public registry, you also have the possibility, you can use authentication into private registries, but you can also import images from local tar archives. So there is no need to upload to a cloud registry. Sarus also integrates with the workload managers, for example, respecting the CPU affinity that Slurm will associate with processes and job allocations, and also the MPI ranks and MPI host names. And then Sarus is able to leverage native performance from GPU and high-speed interconnects, and we will see. We will spend a few more words about that later on. And then lastly, it also enables to access the parallel file systems inside containers, which is instrumental in getting input data into the container and then getting the results outside of the container into a persistent setting. I mentioned a couple of times the command line interface of Sarus, and here we see a direct comparison with Docker. As you can see, the resemblance is a pretty close one. We have a pull command for pulling images, load for importing the tar archives. We have the images command for listing the available images on the system, the RMI for removing images, and of course, the run command to create and run a container. Okay, this is going over our very quick introduction for general introduction about Sarus, and I'll be going over how to some advice and suggestions on how to run MPI and GPU containers on Piz Daint. First, we'll start with MPI. So when running containers with MPI, the first thing that we have to consider is the compatibility with the process management interface of the system we are running on, or PMI for short. The PMI is the technology used by an MPI launcher to communicate with the processes that form the MPI ranks. So yeah, it is this conjunction between the launcher and the processes. By default, on Piz Daint, the Slurm workload manager will use the Cray PMI, which is only understood by the Cray MPI libraries, which are not generically available. So if you come in with an image using a more generic implementation of MPI, let's say Mpis, Mpis, or even the Intel MPI, those will not be able to communicate right away with the MPI launcher. However, the Slurm on Piz Daint also supports the PMI2 interface, which is a much more widely adopted standard. So we can run generic images as they are by telling Slurm to use this PMI2 interface. So not using the Cray PMI default, but using a different process management interface. And we can do so with this --MPI equals PMI2 option to srun. When using PMI2, containers, as I said, will run unmodified, and they will use the MPI libraries from the image. This also means that it's highly unlikely that these very generic MPI implementations will know how to communicate properly with the high-speed interconnect of Piz Daint, and so they will run at a reduced performance. In order to use MPI2 with Mpis and derivatives, no special let's say interaction is needed, because these all Mpis derivatives like Mpis and Intel MPI, as I said, they use PMI2 by default, so they can work out of the box. When using OpenMPI, OpenMPI must be explicitly built with PMI2 support. And here at the bottom of the slide, we see an example of how to configure OpenMPI during the build step on a Ubuntu system. Yeah, so as you can see, as far as Ubuntu packages go, PMI2 header files are available within the Slurm workload manager. So within the Slurm workload manager package. So that's why you see the Slurm references here. Okay, this is one way we can run MPI containers, but we can go one step further. We can go one step further if we leverage ABI compatibility. If you're not familiar with the concept, when two libraries are said to be ABI compatible, it means that an application can be dynamically linked to either of those libraries and still work correctly, because the interfaces at the binary level between the application executable and the shared library are the same. So the libraries that are ABI compatible are interchangeable at dynamic linking time. In particular, in our case, Mpis-based MPI implementations are ABI compatible with the Cray MPI. So Sarus can leverage this property to replace the MPI within the image with host libraries, with the native libraries at runtime while the container is being created. So the containerized applications can run at the full performance of the Cray areas interconnect. And we can do so very simply with the --MPI option to Sarus run. Notice this is a slightly different syntax compared to the previous slide. So since this requires a level of compatibility between the host and the image, we recommend the following MPI implementations when wanting to leverage these native MPI support on Piz Daint. So we recommend Mpis 3.14, Mpis 2 version 2.2, or Intel MPI 2017 update 1. So this is the current recommendation, and as the host native stack evolves, we will be regularly going over and possibly updating these recommendations. Coming now to GPU containers. For GPUs, things are even simpler, because when running on sorry, a helicopter passed over me, so I hope you didn't hear the noise. When running on Piz Daint's GPU nodes, no explicit user action is required in order to enable GPU devices inside containers. They are automatically added by Sarus. So the only thing that is needed is to provide the CUDA toolkit within the container image. And the fastest way to do that is to use the official images provided by NVIDIA on Docker Hub. And I put the link here in the slide. So when writing the Docker file, it means that we can just open the Docker file with this instruction from NVIDIA/CUDA, and then after the colon, just the version of the image with the CUDA toolkit that we want to use. In this case, 11.3 on Ubuntu 2004. It's worth mentioning that the NVIDIA official images are only provided for 3 Linux distributions: Ubuntu, Red Hat UBI, and CentOS. If you want to use different images, like different distributions as base images, you can still do so, but you will have to install the CUDA toolkit through more traditional ways, like through the package manager or the run file. Another thing worth mentioning is that the NVIDIA driver should not be installed in the image, because the driver is tightly related to the hardware. So if you want to keep the image portable, so capable of being used through many different systems, the driver should not be in it. It is rather the responsibility of a container engine like Docker or like Sarus to provide the driver and the device files into the container, depending on the host you are running on. Okay, enough with the slides. Let's see some examples on Piz Daint directly. So some actual usage. Let me transition. This is the window. Okay, so here we are on Piz Daint. And in order to gain access to Sarus, like with all the other applications, we just load the environment module. And here it is. We can invoke the program. Just passing without arguments will print a help message. And now that we have it available, since we are responsible users, we ask for an allocation. So allocation on the GPU nodes, entering the account for my group, and then I will ask for 4 nodes. Here we are, waiting for Slurm to give us our nodes. Okay, we got our allocation. And let's start with the examples. As I mentioned at the beginning, I have prepared 3 different examples. As you can see there, we will have a directory for each of those. We have CUDA SDK samples for GPU usage. We have GROMACS as a real-world application, and then we have the Ozu Micro Benchmarks for MPI, here shortened in Ozu MB. If you're not familiar with the Ozu Micro Benchmarks, they are simply a suite of small programs to evaluate and compare the performance of MPI implementations and network hardware so for example, measuring bandwidth or latencies of message exchange, stuff like that. And we will start exactly with the Ozu Micro Benchmarks. So let's get into the subfolder, and I will be using a container image created with this Docker file. Let me show it to you. So I'm starting with NVIDIA CUDA 11.3 on CentOS, and just installing some compilation tools, downloading and installing Mpis 3.14, and installing the Micro Benchmarks version 5.7, configuring some CUDA integration, and the reason you will see shortly why I'm also using CUDA here, and then setting a working directory, a default working directory for the image for convenience when launching a container. So before actually running a container, we have to pull the image from the remote registry. In this case, the image is stored on Docker Hub. So let's do that. So let's go. Let's clear the terminal a bit. I'm gonna ask for one node because we only need one node when pulling images. The image name is ethcscs/Ozu MB 5.7 Mpis 314 CUDA 11.3.0 and then CentOS. So basically representing the essential components of the software stack in the image. And we just run, and Sarus is contacting Docker Hub and retrieving all the different layers that form an image. So we are pulling, then the layers are being extracted and unpacked. And then finally converted to a SquashFS format. There, the pull is complete. And now we can use the Sarus images command to show which images are available on the system. And here we are. Here we have here on the bottom, we have the image that we just pulled. And you may notice that I also already pulled the images for the other two examples, the CUDA SDK and GROMACS. So we don't have to repeat this process also for the other examples. Okay, now that the image is available, let's run some containers. And I would say let's run some MPI containers. So I'm gonna ask for two nodes, then use Sarus run, just paste in the image name, and then I'm gonna use the Ozu latency program. So Ozu latency performs a series of ping pong message communication between two processes, or in this case on two different hosts, for a variety of message sizes, and it will print the latency of those message exchanges. So it's a simple but very significant point-to-point benchmark. You will notice that I have not entered the absolute path to the program, but I have used a relative path. This is because, as you might remember, I have set a working directory on the Docker file, and Sarus is able to understand those working directory, those workdir instruction. And so we can simplify the command line when launching a container. We're using that as a convenience feature. So here I want to run with the container as it is with the Mpis MPI. Can we do it like that? Not quite, because as I have said before, we need to instruct Slurm to use the PMI2 interface so that the standard Mpis in the container will be able to communicate with the MPI launcher. Let's launch our containers. And here are the results. As you can see, we ran from 1 byte to more or less 4 megabyte message size. And these are the latencies. But we are using Mpis 314 in the image, which is one of those versions which are compatible with the Cray MPI on Piz Daint. So Sarus will be able to inject the native libraries into the container and run at full performance. Let's see how it goes. So first I will remove a PMI2 option from srun and add the --MPI in Sarus run. So why did I remove the PMI2? Because since Sarus will be injecting the Cray MPI libraries inside the container, those will be able to naturally communicate with the default Cray PMI used by the workload manager. So there is no need anymore when using the native MPI to use PMI2. Let's launch our containers. It takes a little bit longer, and here it is. So as you can see, the latency difference when using the native on the bottom and the container and the image MPI on top is pretty significant, but that's what we would expect to be. And the advantage is significant all across the different message sizes. So this gives you an idea of what happens when we actually put high performance components within the container. But we don't have to stop here, because now that we have a way to put the native MPI inside the container, we can also leverage other advanced features of it, not just the performance. For example, we can perform direct message passing between GPU devices. We can communicate directly between GPU memories using the GPU Direct RDMA technology, which is supported by the Cray MPI. Let's have a look. So I will reuse the command, the previous command. In order to enable the GPU Direct MPI, I have to add these environment variables. So Mpis RDMA enable CUDA. There are underscores. I don't know if you can notice them between the all caps words. So Mpis RDMA enabled CUDA equals 1. Then inside the container, as a container argument, I have to add a utility program, which is called getLocalRank. This has nothing to do with Sarus or with the MPI or nothing. This is required by the Ozu benchmarks suite. It's just a way for the programs to correctly associate an MPI rank with a GPU device. And then specifying the CUDA transport to the latency benchmark, and then also specify that we will be using a buffer on the device to another buffer on the device with the capital Ds. Let's run. And yeah, here we go. So as you can see, this is indeed an MPI CUDA program using a send buffer on the device with a receive buffer on the device. The performance is what you're seeing right here. It is higher than the previous run, but now we are no longer communicating between the main memories on the nodes. We are communicating directly between NVIDIA GPUs. So we're skipping the transfer between main memory and GPU memory.
So Alberto, can I interrupt you a little bit?
Yeah.
Because there are a couple of questions.
Yeah, sure. Do you want me? I can have a look at the chat.
There are two questions at the Q&A and one question at the chat.
Okay, so I will get those. I will quickly get, because we have time. I will quickly answer the couple of questions from the Q&A. Michael asks, why does the image has to be pulled on a compute node? Well, it is a recommended policy. You don't need to pull on the compute node, but it is heavily recommended, because if you pull on the login node, you would be like, the login node is shared between all the users. So it might be slower for you. You might be slowing someone else's down. So it is recommended also to have the node, to have a compute node that is dedicated to you. You have a lot of RAM on the compute node, so that also helps speed up the pull process. Michael also asks what does it happen if the MPIs are not compatible? Well, in that case, there will be the component of Sarus that is taking care of the MPI replacement, will check the compatibility between the host and the MPI libraries, and will indeed it will issue you an error saying, look, these libraries are not ABI compatible. I cannot carry on with the replacement. So in that case, yeah, you should still be able to run with the image MPI. So with the image MPI, if you have if you are also compatible with the PMI, with the process management interface of the MPI launcher, as I mentioned. There is also, I see also a question from Jochen in the regular chat. Would Sarus tell me if I can find a compatible MPI in the container? Yeah, I think I partially answered to that before. Yeah, so what Sarus does when trying to find compatibility is looking into the image through the ldconfig utility and try to compare with the native MPI that has been configured by a system administrator. If a match can't be established, Sarus will tell you that I cannot find a library, or that library is not ABI compatible. So let's move on. Let's get back with the examples. I just showed an example using MPI communication, RDMA communication with GPU devices. So, oh, sorry. So let's keep talking about GPUs, and this time with an example more directly representing performance from or usage from a CUDA program. This would be one of the samples from the CUDA software development kit, the CUDA SDK. Let's have a look at the Docker file of the image I will be using. We're starting from NVIDIA CUDA 10 development and installing the CUDA samples through the package manager. You might notice from the package manager syntax that this is a Ubuntu-based image compared to the previous one that was CentOS 8. And I just compile some of the samples using the make file and the make program. So a very short Docker file. The image is already pulled, as I said before, so I can run right away on one node. And I enter the image name, which is ETH-CSCS CUDA samples 10. And then I'm going to use the sample program I'm going to use is called Embody, which performs a simulation of gravitational interactions between a group of bodies. So it represents the Embody problem, hence the name. I'm going to be running on benchmark mode in double precision. and with 200,000 bodies. So that we give the GPUs on Piz Daint some work to do. Let's run. Here it is, the program is completed. As you can see, it correctly, from the output, it correctly identified the Tesla P100 in the compute node of Piz Daint. And the program was able to achieve over 3,000 gigaflops, so slightly over 3 teraflops of performance. And these were double precision flops. So it is pretty much what this benchmark program will achieve also natively on this kind of hardware. So and as you can see, no specific option, no specific instruction was needed to enable the GPUs in the container. It is all handled through the interaction with Slurm and Sarus. Now we've seen an MPI example, we've seen a GPU example. Let's put both of those programming models together to run a real application, which would be GROMACS. If you're not familiar with GROMACS, GROMACS is a quite popular simulation package used for classic molecular dynamics simulation. It was initially developed for biological molecules, but it's been increasingly used also for non-biological systems. Let's have a look at the Docker file. Now, this being a more fleshed out application, it's a little bit longer. I'm going to start from the NVIDIA CUDA 11.2 on CentOS again, installing a couple of additional repositories and dependencies. I'm going to use Mpis 3.14 again, and then downloading GROMACS 2020.4, configuring integration with CUDA, with MPI and some instruction, and setting some environment variables for finding the executables within the image. Okay. So since GROMACS is like a real program, I wanted to show like a more regular way of using an actual program. So, or a simulation program where you have input data that you have to provide to the application, and you also want some results to get out of the application. So in this case, the input data is represented by this lignocellulose RF TPR file. And this comes from a praise test case for GROMACS. So we need to get this file, as you can see, resides on the Scratch file system of Piz Daint, and we need to get that into the container. In the same way, we need to get the results files from GROMACS to out of the container and into our file system. Let's see how we can do that. How we can communicate communicate files from the host system, the host file system, and the container. So I'm going to run on 4 nodes now. Sarus run, require once again the native MPI support. And then I'm going to use the mount option. The mount option will make available file systems and directory from the host into the container. So that's the way we will be able to exchange data and files between the entities. I'm going to request a bind mount, and I have to specify the source, so the path on the host of the location I want to mount. And here I'm currently on Scratch, so our input files are on Scratch. So I'm gonna mount my Scratch folder using the environment variable. Then I have to provide the destination, which will be the path within the container where these files will appear. And nothing wrong in reusing the Scratch path once again, also because there is no Scratch in the container image. And then I will use the work dir option. So this option will set the initial working directory in the container. In this example, I'm going to use it as a convenience feature because by default, GROMACS will write results file in its current working directory. So if I set the work dir with this option to be the location I am already in, which would be, in this case, would be Scratch, which is, by the way, I just mounted inside the container with the previous mount option. If I move the working directory here already, I don't have to explicitly enter the paths for the results files of GROMACS. And I can, and can make the command line a bit simpler, a bit more readable. So now let's enter the image. ETH-CSCS GROMACS 2020.4 with CUDA 11.2.0, Mpis 314, CentOS 8. Now we can get to the actual GROMACS command line, which is GROMACS MPI, the MD-run program to perform a simulation. With the -S we provide option, we provide the location of the input file. And with -G, I also require to output a log file with all the information about the simulation. I'm gonna run with one OpenMP thread for 100 simulation steps. Let's launch the simulation. Here it is, GROMACS is in action. And as you can see, we have 4 MPI processes, as we requested 4 MPI ranks. And here it is, the GROMACS run has been completed. When we get some information about the work clock time and the performance. So now we can just inspect the directory, and now we see that before we only had the Docker files and the input file, but now we have the output files created by GROMACS residing on the Scratch file system. We have the output configuration, the energy, the log, and the simulation state at the last step. We can also inspect these files if we want to be absolutely sure. So this is the log file of GROMACS with all the details of the simulation that we just performed. The simulation was carried out inside a container, in containers running on 4 MPI nodes, on 4 different nodes, but now they are available on the host and then can be persisted on the host. Of course, this is Scratch. You should move to other file systems for more long-term storage, as the CSCS policies advise. Okay, this basically concludes all the 3 examples I wanted to show you. We went from simple MPI point-to-point benchmarks over to a GPU benchmark, and then we put everything together into a real MPI plus GPU application. Because GROMACS is also GPU accelerated and also performing some data I/O. So let me just get back to the slides for wrapping up. If you want to know more about Sarus, we have a page on the CSCS user portal targeting more specifically instructions and also providing more guidance on how to run on Piz Daint. Sarus is an open source software, and it is available, the code is available on GitHub. If you want to deep dive into it a bit more, we have a full user documentation on Read the Docs. And for the more formally inclined of you, we also have published a paper at an ISC workshop almost 2 years ago now. And these are the references with the DOI. So this document provides a more formal introduction to Sarus and the highlights and the motivation behind it, and also provides more results on larger scale, on tests at larger scales that we performed. This basically concludes my presentation, and we have 10 minutes to the top of the hour, so we have quite a bit of time for questions.
There are already some in the
yeah. So let me thank you once again for your attention, and let me just recover the chat windows for the questions. Okay, so I see that the first question that I see is from an anonymous attendee. Okay, can we have a normal Docker entry point script? No, so yes, you can. Sarus supports entry points from Docker images, so you can indeed have specify entry points in the images, and you don't have to. And if you provide further arguments on the command line, those will be passed to the entry point scripts. I see a question from Eduardo. What are your suggestions on how to profile an app running inside a container? Is it possible to run Craypat or vtune? Though I'm not an expert on that, it is not quite easy. Let me think a little bit. I don't know. I wouldn't know how to do it. So I know that there have been some experiments doing it. What the most difficult thing to do is to use an external tool and connect inside the container. If you already have a profiling tool within the container, then that is easier to achieve. But from outside, an outside tool and profiling something in a container, that is something that requires more work in order to do it more elegantly. I know that there has been some success, I think, with debuggers, like using, for example, DDT or something like that to debug containers. But with profilers, I'm not too familiar with that. Enrique asks why the RDMA results were slower. Comparisons against nickel. No, I don't have any experience in comparing results. This was an example just to show you how you can enable the RDMA functionality. But I'm not an expert on the actual RDMA technology. So I wouldn't be able to justify other than, yeah, it is lower than communicating between main memory, but you are also going directly through. You're doing, let's say, the distance you're covering is larger because you're going directly from GPU device to GPU device. So qualitatively, I would say that some more latency compared to a direct memory to memory transaction, I would expect it. But as I said, I'm not an expert on networks and RDMA, so don't take my word for it. As a non-expert, I would it doesn't ring a red light for me. I see a couple of questions from Gerhard in the chat window. The examples are also online. We had these specific examples that I show today are not yet online, but we have on Read the Docs, we have a cookbook with a lot more examples similar to the ones that I've shown. So MPI, Embody, GROMACS, also some TensorFlow or a CFD applications. So we have more examples on Read the Docs in what we call the Sarus cookbook. So you can check on those if you want. Also another, there are one or two examples also in the CSCS user portal. And we will probably also eventually we will put also the examples like those that I have shown here. We will get them online as well. Sarus cannot run rootless yet because of a specific technique that we leverage in order to mount the images at scale and achieve scalability and performance when mounting images on, like for example, on hundreds or thousands of nodes. But so no, Sarus cannot run rootless. Even that, we know all the advantages of rootless, and we are considering our steps forward. At the moment, we are not planning a Sarus exec command because for now, Sarus containers are disposed after they finish execution. So the exec command would entail that the Sarus containers have a kind of persistency, and so that's not possible at the moment. So no, we're not supporting a Sarus exec command. Oh, you will be especially interested in the Embody example. Yeah, that, as I mentioned, that is available in the cookbook on Read the Docs, so you will be able to find it. Okay, so last question from Michael. What about debugging? Yeah, I also think I already answered this before. Like I said, for example, in the CSCS user portal, there is a page about the DDT debugger, and that page also has there are also links on how to debug containers with DDT, with Sarus, and I think also Singularity. So there are resources, for example, for using MPI debuggers on the CSCS user portal. Okay. We have 4 more minutes. If I don't see any more question coming in, let me just get a quick drink. Okay, if there are no more questions, I would say we can conclude the webinar here. We are slightly earlier, 3 minutes to 11 a.m. So let me thank you once again for attending this webinar, for your attention, and for your interest in Sarus and the tools offered by CSCS. And I think that the recording of the webinar should be available shortly or relatively soon after today. And if there's nothing else, no more questions coming in, as I said, thank you again, and wish you all a good morning and a good day. And we'll see you soon.